Hi all, it's chapter 2 now, Earth's physical systems. This is another one of those chapters that's going to be quite a bit of review for you. So hopefully when you learned your chemistry sections in physical science or earth science or chemistry, you can recall all of that information right now. So we're going to start with matter. It's important to understand matter and the conservation law of matter. And remember, matter is anything that takes up space. Solids, liquids, gases are the states of matter. It's around, it's everywhere. The law of conservation of matter says that you can't destroy it. It just changes its form from one form into the next. That water, when it gets cold, becomes ice, etc. Okay, so look through that if you don't remember those key features. Same thing here with the atoms. Don't forget the parts of an atom. When we start to do more energy talks and discussions, you're going to have to recall a lot of this. So protons inside the nucleus along with the neutrons, which are neutral. Outside of the nucleus is the electrons, which are found in the electron cloud, and those are negatively charged. If for some reason an atom is missing with a different number of neutrons, we call that an isotope. So we see isotopes when we look at like carbon-14 or carbon-12, and you've heard about that with dating of bones and fossils and everything else. So understanding what isotopes are, they have the same element, but they will have a different number of neutrons, so their atomic mass will actually slightly be different. This is important for when we actually start to talk about nuclear fusion and nuclear fission. Radioisotopes, as they start to decay, they're going to actually start to shed their atomic particles, and when that happens, they're going to emit the radiation. And when we start to think about nuclear power plants, we have to be worried about the uranium byproducts that are created. How long that uranium is going to actually give off the nasty radiation. What are we going to do with it? Understanding half-life is really important as well with that. So when we get into some of those units, we're going to actually start to calculate half-life, the time it takes for the atom to actually decay halfway. So we can figure out how long a particular radioisotope is going to be on Earth and be an issue for us. Okay. Another big thing that goes along with water pollution and soil and everything else is pH. Go back to your chemistry days. Remember what pH is? It's the amount of those H+ ions that you're going to see. So remember, pH goes from 0 to 14. From 0 to 6, those are the acids. 8 to 14 are the bases. Anything that's neutral, so the same amount of OH and the same amount of H+ ions balance out, that's neutral, that's your pure water. As you get to 0, you become more acidic. As you get to 14, you become more basic. These guys are going to have a lot of H+ ions. These guys are going to have a lot of OH negative ions. Okay, so we're going to see that again and again and again in this class. Remember, this is a logarithmic scale. So when we look at that, 6 is 10 times more acidic than 7. We keep going logarithmically. Hydrocarbons. Hydrocarbons are anything that's made up of a hydrogen and a carbon atom. We see this with crude oil, petroleum, fossil fuels, coal, natural gas. Those are all hydrocarbons. So if you were to look at them chemically, they're carbons bonded with hydrogens. And when we burn fossil fuels, the interesting thing that happens is we rip the carbon starts to get broken and disconnected, and that actually is going to produce the energy that we get when we heat our house or do the combustion that runs our car. The broken carbons then can actually connect with two oxygens, and they start to make something called carbon dioxide. And if we know anything about carbon dioxide, it creates a lot of problems for us in the atmosphere. So the good thing about hydrocarbons, they give us our energy, they warm our house, they do all that stuff. But one of the negatives with hydrocarbons is actually the pollution created through the release of carbon dioxide. Now that carbon dioxide can be dissolved in the ocean, which will make carbonic acid. Some are taken in by trees to make tissues in the process of photosynthesis. Some carbon, actually we call it carbon sequestering in that case, Some will stay in the atmosphere and get trapped as heat, and that can actually lead to global warming. If you don't remember your DNA from biology class, proteins are made up of amino acids. DNA and RNA code for those proteins, so we will see a little bit more of that. This class is a lot of chemistry and a lot of biology. Okay. Energy. Energy is your ability to just change something from one form, again, into another. You can't create it, you can't destroy it, you just change its form. And that's the first law of thermodynamics with energy. Two of the types of energy that we talk about mainly, kinetic and potential energy. If you remember your kinetic and potential energy from middle school, which you should, kinetic energy is movement or motion, and potential energy is the energy of position. So if we look at this girl over here, she is gaining energy through potential energy, the food molecules that she's eating. Eventually, she's going to transfer that potential energy into kinetic energy when she uses that energy later to go rollerblading. I'm going to bring you back to the good old days again of biology. A little bit of photosynthesis for you. So, visible light, which we see up here, the rainbow, is emitted from various things around you. They reflect that color to your eyes so you're able to see it. So green leaves reflect green and they absorb all the other colors of the rainbow. For plants that are doing photosynthesis, they need light energy, which is made up obviously of the visible light spectrum. If you remember the light and the dark reactions, or the Kelvin cycle of photosynthesis, it'll come in handy. Remember, in the light reaction, you have light energy that comes in with water. That light energy rips the H's away from the O's. The O's get released as waste. The H's then continue on to the Kelvin cycle. In the Kelvin cycle, CO2 is taken in by the leaf, joins up with that H, and produces sugar in the form of, C6H12O6. So there's your CO, and then your H comes over from the other side. So there's your little rundown of your photosynthesis, your Kelvin cycle, and your light reaction. The interesting thing about light, though, is wavelengths travel at different distances. So green, remember, gets reflected. The reds and the blues can actually travel different depths. So if this was happening in water, this little lily pad here doing photosynthesis, red light is actually only able to travel about 1 meter underwater. Blue light is able to travel to greater depths. So there are certain plants that are actually able to do photosynthesis better with blue lights, some that are not. So photosynthesis usually only occurs in the top layers of water. Make sure you review the equations for respiration and photosynthesis, kind of knowing what's coming in, what's going out, the products and the reactants. So again, respiration can't happen without photosynthesis, and photosynthesis cannot happen without respiration. A little bit more science. You should have learned this in middle school. Earth, we know, has a core. It's got this lovely little mantle here. The mantle is made up of a couple of different layers, the asthenosphere and the lithosphere. We know that there's the magma in here that can cause plates like the continental plates and the oceanic plates to move. And when they move or shift, we call them boundaries. So there are 3 types of boundaries here. The first one's convergent. Convergent plate boundaries happen, here, I'll take a picture over here. Look this up. There's the convergent. There are 2 types of convergent plate boundaries. To converge means to come together. So when you have a continent and a continent coming together, they're going to actually uprise and create a mountain collision. And this is actually what's happening to form the Himalayan mountains. If you have an ocean and a continent coming together, the cool thing about that is the oceanic crust is more dense than the continental crust.